Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
Okay, so for years, it's felt like quantum computing has been this perpetual science fiction promise, right? Always 5 to 10 years away. You hear about it, you nod, you think, cool, but when is it actually going to do something?
Totally. It's been the ultimate tease, stuck in this academic sandbox, solving theoretical puzzles that, while important, never quite felt like they were tackling real problems in the messy world.
Exactly. But then IBM drops this bombshell. They didn't just simulate some abstract math problem, they simulated a real world's material, a magnetic crystal, and the results matched actual physical experimental data, not just another computer's output, but reality.
That's the kicker, isn't it? It's not just good on paper. It's a direct quantitative match with neutron scattering experiments, which is the gold standard for probing material properties. This isn't just a step, it's a leap from concept to a tangible, verifiable scientific instrument.
So they actually did it. They finally took quantum out of the sandbox.
It certainly feels like it. This collaboration, spanning across major research institutions like Oak Ridge and Los Alamos National Labs, plus Purdue and Illinois, with IBM's tech at the core, it's a powerhouse effort that just delivered concrete proof of concept. It feels like the goalpost just moved significantly.
All right, so let's unpack this. The material at the heart of this breakthrough is called potassium copper fluoride, or KCuF3, which, let's be honest, sounds like something you'd find in a dusty chemistry textbook. What is it, and why was this particular material such a challenge for classical computers?
You're right, KCuF3 isn't exactly a household name, but to a condensed matter physicist, it's famous. It's considered a near-perfect real-world example of what they call a one-dimensional Heisenberg spin chain.
A one-dimensional Heisenberg spin chain. That sounds intimidating. Break that down for us. What makes it so hard to simulate?
Okay, so imagine every electron in this material has a quantum property called spin. You can loosely think of it like a tiny bar magnet that can point up or down. Now, in KCuF3, these tiny electron magnets aren't just sitting there. They're strongly correlated, constantly interacting with their neighbors in a chain.
Like a line of dominoes, but instead of falling, they're influencing each other's magnetic direction.
A great analogy. Now, to accurately simulate this system on a classical computer, you'd have to account for every possible configuration of all these electron spins at once. And here's where the problem explodes, what they call the curse of dimensionality.
Exponential complexity, right? We've talked about this before.
Exactly. For a small number of atoms, a supercomputer can brute force it. But as that chain of interacting spins gets longer, the number of possible quantum states becomes astronomically large. It quickly exceeds the memory and processing power of even the most powerful classical supercomputers on Earth. You'd need more memory than there are atoms in the universe.
So classical methods are basically stuck making approximations, which means you're not getting the full picture, especially when it comes to those subtle quantum effects that really dictate how a material behaves.
Precisely. There's so much neutron scattering data on magnetic materials that isn't fully understood because of the limitations of approximate classical methods. Researchers are, in a way, flying blind.
And that brings us to the gold standard benchmark, neutron scattering. That's how they validated the quantum simulation. How does that work?
Neutron scattering is a powerful technique used at facilities like Oak Ridge and Los Alamos. They fire a beam of neutrons at a material sample. Neutrons are special because they're neutral particles, so they can penetrate deep into the material without being deflected by electrical charges. But crucially, they do have their own spin, so they interact directly with the magnetic fields of the electrons inside the material.
So they're like tiny magnetic probes that can get right in there without messing things up too much.
Exactly. By measuring how the neutron's energy and momentum change after they scatter off the sample, scientists can literally deduce the arrangement and collective behavior of those electron spins. It provides a direct physical measurement of the material's quantum properties. It's an unimpeachable yardstick for accuracy.
And the IBM quantum computer was able to calculate these complex spatiotemporal correlation functions, which then reconstructed the material's dynamical structure factor, which is exactly what a neutron scattering experiment measures. That's why the match is so significant.
As Travis Humble, director of the Quantum Science Center at Oak Ridge National Lab, stated, quantum simulations of realistic models for materials and their experimental characterization is a major demonstration of the impact quantum computing can have on scientific discovery workflows. That's high praise from someone who literally works with the physical reality.
All right, so this sounds like pure quantum magic, but the report makes it clear this wasn't just a quantum victory. IBM's branding this as quantum-centric supercomputing. That's a mouthful. What does that actually mean?
This is a crucial point, and it's a reality check on the hype. It means the hero here isn't just a standalone quantum processing unit. This is a pragmatic, hybrid model that acknowledges both the strengths and weaknesses of classical and quantum computing today.
So it's not the quantum computer doing everything by itself?
Far from it. Think of it like a specialized team. A quantum-centric supercomputer tightly integrates quantum processors with traditional high-performance computing resources, your CPUs and GPUs. The core idea is a feedback loop, where each type of processor does what it does best.
So who does what in this team?
The classical supercomputer acts as the brain. It handles the overall problem setup, manages the data, and does all the parts of the calculation that don't involve complex quantum mechanics. Then, when it hits a computationally intractable quantum problem, like calculating those electron spin interactions in KCuF3, it offloads just that part to the quantum processor.
The quantum processor is the specialist.
Right. The QPU performs its specialized quantum-intensive calculation, then sends the results back to the classical computer. And this can be an iterative process. The classical machine refines its parameters based on the quantum results, then sends new instructions back to the QPU.
That's a really smart workaround. It's like breaking a huge, impossible puzzle into smaller, manageable pieces and only giving the quantum machine the pieces it's uniquely designed to solve.
Exactly. It's how they're getting value from current quantum hardware without having to wait for these futuristic, fully fault-tolerant machines. A big part of the success here was the tangible improvements in their hardware, which helped manage the challenges related to noise and error.
I know errors are the bane of quantum computing. What kind of hardware improvements were key to this breakthrough?
The success was indeed a combination of the clever hybrid architecture and continuous improvements in quantum hardware. Managing noise and errors is paramount in quantum computing, and IBM has been making steady progress in making their qubits more stable and reliable, which was crucial for this KCuF3 simulation.
So it's a combination of this clever hybrid architecture and better, more stable quantum hardware that made this possible. They're also improving the software stack, like Qiskit, to help mitigate errors, even on noisy hardware.
Yep, it's an ecosystem approach. But here's the reality check, right? As exciting as this is, the report reminds us we're still very much in what John Preskill called the NISQ era, noisy intermediate scale quantum. What does that really mean for practical applications today?
The NISQ era. The constant reminder that we're not quite at Star Trek levels yet. What are the key limitations that NISQ implies?
NISQ devices have three main constraints. First, intermediate scale means a relatively small number of qubits, typically 50 to a few hundred, though some are now topping 1,000. This limits the size of problems. Second, they lack full-scale error correction. There aren't enough qubits to fix the inevitable errors that occur.
And then there's the big one, noisy.
That's the real tyrant. Qubits are incredibly fragile. They are exquisitely sensitive to their environment. Tiny fluctuations in temperature, electromagnetic fields, even vibrations can disrupt their delicate quantum state. This is called decoherence. It's basically noise, and it introduces errors into the computation. The longer a calculation runs, the more errors pile up until the result is just meaningless.
So it's like trying to have a very precise conversation in a really loud, echoey room where everything keeps getting garbled.
Perfect analogy. Because of decoherence, qubits have very short coherence times. The window where they can maintain their quantum state is fleeting, often just microseconds. This severely limits the depth of a quantum circuit, meaning how many sequential operations you can perform before the quantum information is just lost.
So this KCuF3 simulation, while groundbreaking,
was still performed within those NISQ limitations. It wasn't a huge, complex problem by future quantum standards.
Exactly. It was a problem just big enough to be intractable for classical methods without approximations, but still manageable enough for today's noisy quantum hardware, especially with that hybrid approach. The holy grail for the long term is fault-tolerant quantum computing.
Which means building logical qubits out of many physical qubits to essentially make them self-correcting, right?
That's the idea. You encode quantum information across a group of physical qubits redundantly. Special syndrome qubits detect errors without disturbing the actual data. If an error is found, it can be corrected. It's error correction, but vastly more complex than in classical computers.
And the overhead for that is massive. Thousands, even tens of thousands of physical qubits for one stable logical qubit.
Precisely. Building such systems is a huge leap from where we are. So while KCUF3 is a landmark for the NISQ era, scaling this success to simulate genuinely revolutionary new materials, like a room-temperature superconductor, will require machines with many more qubits and robust error correction.
So where does this KCUF3 breakthrough lead? Simulating one magnetic crystal might seem esoteric to most people, but the report says the implications are vast for multi-trillion-dollar industries. Who cares, and who wins from this kind of advancement?
That's the critical question, isn't it? This experiment is a powerful proof of concept, a tangible signpost pointing to a future where quantum simulation could become an indispensable tool. If this hybrid method is repeatable and scalable, it could dramatically accelerate research and development cycles in areas that are currently bottlenecked by classical computing limitations.
Give us some examples. Where are we going to see this impact first?
Top of the list is pharmaceuticals and drug discovery. Discovering new drugs is incredibly time-consuming and expensive. The core challenge is understanding how a potential drug molecule interacts with a target protein in the body. These interactions are fundamentally quantum mechanical.
And classical computers struggle to model them accurately, so they rely on approximations and endless lab experiments.
Exactly. Quantum computers promise to simulate these interactions precisely. Imagine scientists being able to accurately model the electronic structure of molecules to predict drug efficacy, identify potential side effects early, or even design entirely new molecules with desired properties from scratch, what's called de novo drug design. We're already seeing studies applying hybrid quantum approaches to things like modeling prodrug activation for cancer treatments. This IBM result just brings that future closer.
That's huge. What else?
Advanced materials and battery technology are next. The hunt for materials that are lighter, stronger, more efficient, think alloys, solar cells, or better batteries, is all about understanding the quantum behavior of electrons.
And battery tech is a massive one, especially with the EV revolution.
Absolutely. Automakers like Hyundai and Daimler are already partnering with quantum firms. They want batteries that are more energy-dense, for longer-range EVs, faster charging, and safer. Quantum simulation could allow them to virtually test thousands of new material combinations to find the optimal chemistry for the next generation of batteries, a task currently impossible.
So instead of years of trial and error in a lab, you could run simulations in days or weeks.
Potentially, yes. And then there's energy and catalysis. Many industrial processes, from making fertilizers to developing cleaner energy, rely on catalysts. Designing better catalysts is a quantum chemistry problem. Imagine understanding nitrogen fixation, how certain bacteria convert atmospheric nitrogen into ammonia. That could lead to dramatically more efficient fertilizer production, with massive impacts on global agriculture and energy consumption.
So instead of years of trial and error in a lab, you could run simulations in days or weeks.
Potentially, yes. And then there's energy and catalysis. Many industrial processes, from making fertilizers to developing cleaner energy, rely on catalysts. Designing better catalysts is a quantum chemistry problem. Imagine understanding nitrogen fixation, how certain bacteria convert atmospheric nitrogen into ammonia. That could lead to dramatically more efficient fertilizer production, with massive impacts on global agriculture and energy consumption.
So in essence, this isn't just an obscure science experiment. This IBM announcement is a very loud signal to these industries that the timeline for quantum computing's impact is accelerating. It's a move from abstract promise to a concrete, verifiable demonstration of scientific utility.
It's an inflection point. The sandbox is officially being left behind, at least for certain types of problems.
All right, let's tie this all together for our listeners. What are the key takeaways from this landmark announcement?
First, we've hit an inflection point. A quantum computer has successfully simulated a complex, real-world material, and its results were validated against gold standard experimental data. This is a major milestone for quantum computers as viable scientific instruments.
Second, the pragmatic path forward is clearly hybrid. This breakthrough wasn't a pure quantum play. It was quantum-centric supercomputing. Classical supercomputers and quantum processors working in tandem, a feedback loop. That's the key to getting value from today's noisy quantum hardware.
Third, we still have to temper our excitement. We are firmly in the NISQ era. Today's quantum computers are noisy and error-prone, which limits the complexity of problems they can solve. The grand challenge of building truly fault-tolerant, large-scale quantum computers with robust error correction is still a long-term goal.
And finally, this gives us a tangible future for R&D. This KCUF3 result is a concrete proof of concept for industries like pharmaceuticals, advanced materials, and energy. It makes the future where quantum simulation accelerates the discovery of new drugs, more efficient batteries, and novel materials feel much more tangible and imminent.
It truly does.
So the question I'm left with is this. If this is what the NISQ era can deliver with a hybrid approach, what will those fault-tolerant machines be capable of? And for businesses, how do you start strategizing for a future where some of your most intractable R&D problems might suddenly become solvable?
That's all for Tech Disruptions. Thanks for listening. We'll see you next time.
Stay curious out there.